Hi there, this is Math 145, Section 3.2. And what we're doing here is looking at, again, a set of data, right? In 3.1, we talked about where the center of that data is. We looked at two main ways to do that, finding the mean and the median of a set of numbers, right? So in that section, we answered the question, where is the data centered around? Well, here we're asking ourselves, how spread out is it? So now we know the center. Can we determine if the numbers are pretty close together or are they spread out far from each other? And that is what they call dispersion. We're going to look at range, standard deviation, and relatedly, variance. Variance and standard deviation are very similar. In fact, one is simply the square root of the other. So really the main two ones are range and standard deviation. Okay, so what I would like you to do is read that over. Go ahead and read that definition of the range and then try out it for number one and do what it says. So then we'll come back together. Pause me down, of course, and then we'll come back. Okay, so here I am back again, and I just wanted to point out that there was a sentence here that points out that all the data must be quantitative. You do not find range or standard deviation of qualitative data. For instance, the answers to what is your favorite movie, nothing in 3.2 will be relevant there. Okay, so the first one we are dealing with as far as dispersion is the range. And it simply says the range of a variable is the difference between the largest value and the smallest value. And of course I have my formula here. Number one tells me to do that. Here are my 7 employees of a startup web development company and their travel times to work in minutes. It says find the range, and all I did was pick out the largest value and the smallest value and subtract them, and I got 38. So I could say the range of travel times to work is 38 minutes. And you'll notice I also attached a units on that as well, as I was showing all the time I was doing 3.1 as well. So let's read this over. Okay, definition is a little bit daunting, but not to worry. If you just think of it as the average distance each value is from the mean, that is very helpful. Let's look at this. Now, this is population standard deviation, which is to say it's about population data. On the next page, you're going to see nearly the same formula. It differs ever so slightly, but that will be for sample data. So here is if I got my data from a population. And again, I'm thinking about how the data values could be thought of as x sub 1, x sub 2, x sub 3, all the way up through x sub capital N, because capital N, remember, was the population size. So let's kind of picture, like, if I had a whole population and I said, get their ages, right? So this would be the age of person 1, the age of person 2, the age of person 3, all the way through the age of that very last person. Okay, so back to the formula. The population standard deviation of a variable is the square root of the sum of squared deviations about the population mean divided by the number of observations in the population n, which is kind of weird, right? They're trying to explain exactly what they're doing down here in the formula. So it feels weird. And then they basically just restate it here in that last sentence. So let's quickly get over to the formula itself. First of all, it's going to be represented by sigma. This is the lowercase Greek sigma. And that you'll see on your calculator too when we output one variable stats. We saw it, in fact, when we did 3.1 notes earlier. Here's the formula. It basically says, take each value, subtract off the mean, and then square that. Do it again and again. Take each value, subtract off the mean, and square it. and do it dot, 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 dot until you do it to the very last one. Okay. And then you're going to add them all up. See all these plus signs in here? And then divide that by capital N. That's what the big thought bubble here is saying. That is technically the variance. When you square root it, you get the standard deviation. So then you'll see the formula says square root that, and that equals sigma. So sigma is the population standard deviation. And you'll also notice that to shorthand notate the plus signs all along, they used this sigma notation here, this capital sigma notation that you saw. Whoops, that's an ugly sigma that you saw the other day. I told you in 3.1 we were introducing ourselves to sigma notation, because in 3.2, or I think at that time I said just later, we'll see some more complicated stuff. This is more complicated. That's what I was talking about. So there's our formula. And we're going to do it by hand a couple times in the notes and once like in a worksheet. And then after that, I'm not going to expect you to do this stuff by hand. So let's move on from here and go to the next page. Okay, as it says here, that's all well and good, but you may see an equivalent. It's called the computational formula for population standard deviation. I simply mention this because if you see this online somewhere, I don't want you to get completely confused. It does do the same thing as the previous formula on the bottom of page 1. It just looks a little different. Anyway, some people think that this is easier to do if I had to do this thing by hand, which again, we're not going to do it by hand much, so it doesn't much matter. All right, now we have the sample standard deviation. And again, this is going to be sample data. So let's pretend this data came from a sample, not an entire population, but rather a subset of that population, right? So I'm going to call those data values x sub 1, x sub 2 through x sub lowercase n. And I'm using lowercase n because, again, lowercase n was the sample size, or how many people or elements that I have in my sample. So we are going to define S to be the sample standard deviation. It talks about this, it's the square root of the sum of the squared deviations, blah, 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 blah. But notice how it's divided by n minus 1. Instead of dividing by n, we divide by n minus 1. There is a reason for that, but I'm not going to get into it right here, right now. Just know that the formula for standard deviation, if it's population data, differs ever so slightly than if the data came from a sample. So it's important that when you calculate standard deviation, you know if your data is population or sample data. And in problems in MyMathLab, they will make it clear. They will either imply that it's an entire population or imply or outright say that this is a sample. Okay? In each case, we're going to take each value, subtract off the mean, square, take each value, subtract off the mean, square, dot, 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 do it again, and then add them all up, divide by n minus 1, square root it, and I get the sample standard deviation. And once again, for the computational formula is down here as well. So there's that. We were talking about resistance before. Let's talk about that a little bit. Is it resistance? Since the range is found by subtracting the minimum and maximum values, well, you got to say it's pretty much affected by those extreme values, isn't it? So we say the range is not resistant. The standard deviation uses all of the values in its calculation, much like the mean back in 3.1. Therefore, it's also affected by extreme values and is not considered resistant. So neither the range nor the standard deviation are resistant measures of dispersion. But we will, however, be getting a resistant measure of dispersion later on in another section. So that will be addressed. Okay, so number 2 is about giving you a chance to do this standard deviation stuff by hand. Again, we're going to do it here by hand, and then I've got a worksheet that you're going to do it once or twice by hand, and then no more. After that, I expect you to always put your data in the calculator or StatCrunch and do your calculations there. Even though MyMathLab will probably imply that you're supposed to be doing this by hand. Now, here's what we have for number 2. I have a sample data set. So this came from a sample, which means I am going to find S and not sigma, which was the population standard deviation. And remember, it had a slightly different formula in that we're going to divide by that n minus 1. So we got to figure out what that is in the end. Okay, so let's just say I got a sample of maybe 6 people, right? And these are their ages. First person's 12, first person's 16, or second person's 16, excuse me. Third person's 18, right? And so forth. So here is doing this by hand. I'm just going to do a couple of them actually, and then I'll let you pause me down and complete it. So the formula says first of all, I did find the mean. I just averaged those 6 numbers, and I did find 19.3333. So I am going to take each value and subtract off the mean, and then square that. And I'll round that, okay? I rounded that to 53.78. And now I'm just gonna keep doing it again and again. So on the next line here for the data value of 16, I'm gonna once again subtract off the mean and square it. And I am going to round all of these numbers to 2 decimal places because that should be enough. 11.11 it looks like. And I'm going to keep going. And go ahead and pause me down here and see what your numbers look like, and then you can come back and check me. Okay, so first off, I completed my table here, and you'll notice that if a data point like 12 is fairly far from the mean, this number here, this 53.78, is pretty large, isn't it? But like when you get to 20, the data point 20, it's pretty close to the mean. And so that only contributes 0.44 to this total. And that's basically trying to show you how this is really truly measuring how far each number is from the mean, right? We're going to add up all of these numbers here. And when you do that, you get the total. When I use sigma notation for that, I get that total. I now need to divide by n minus 1. And so I come over here asking myself, well, what is n minus 1? Well, n here was the number of elements in my sample, which was that 6 numbers. And so n minus 1 would be simply 5. So I divide this 133.33 by 5, and I got about, let's change these approximately equal signs, 26.67, rounding that. And then I square rooted that like it told me there on that final line, and I got about 5 point, and I'm going to say 5.2. Now, my calculator, more got 5.1639, blah, 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 blah. But I'm going to round this to 1 more decimal place than I had in the raw data. And that was just a convention that we saw mentioned in 3.1 notes that I'm carrying over here. So I'm going to say the standard deviation of this six numbers is 5.2. If I had a units, like if these were really, the ages of people or, their income in thousands of dollars or whatever it was then, I would attach that to the standard deviation. But these were just rather meaningless numbers just to play around with. So there's that. I also want to show you how that output looks on the calculator to remind you of that. We actually did do this process when we did means and medians, but I'm going to show that screen. Go ahead and do this on the calculator, and then I'll show you my end screen so that you can check yourself. Pause me down. Okay, so I showed the process of actually making the calculator do this one variable stats thing in 3.1 notes. So I did not re-show that here, although I am showing my end screen. And I want you to notice that you can verify that the X bar really is 19.333333. And I want you to notice S sub X here. Knowing it's sample data allows me to pull out that S sub X from my calculator in the future. And you'll notice it is what we ended up with. Now, I will tell you this. There is a population standard deviation given as well. Again, the calculator does not know if the data came from a population or sample. And since the formulas are different, they've got to recalculate both, or they've got to calculate both. So this sigma of X is the population standard deviation. If you knew the data came from a population, you would choose the 4.71. But of course, this time it was sample data, so we're choosing that 5.16 thing. I'll cross that off. But be aware of that. Okay? So that's standard deviation, both by hand and looking at it on your calculator. Another little thing, they do give you sigma x and sigma x squared. If you wanted to do the computational formula, remember those alternative formulas that I gave you back on page 2? So that's why the data is outputted that way. But for our purposes, for our class, I am not requiring that you do the computational formula. I just gave it to you for reference. And definitely, you know, after you do the worksheet here with this section, I don't want you to do this stuff by hand anyway. You're just going to stick the data in your calculator and pull out either S or sigma, depending on if you know it's sample or population data. Okay? Okay, here on page 4, I've got the instructions for StatCrunch, and I'm going to open up a video. I'm going to play you a video that shows this whole process that you see written up over here. I also do want to show you how you can get it to give you the standard deviation if it's population, but you have to ask for it special. So you kind of have to be aware of that. Look at that paragraph there and watch my video. Okay, so you should read the question. It basically tells me that these are a sample of 7 flights' flight times. And of course you've got the numbers there, and it says compute the range and sample standard deviation. The range is pretty easy to do. You just subtract lowest number and highest number, right? You don't really need StatCrunch to do that. But what we're going to see is the StatCrunch process of finding the sample standard deviation. And I'm also going to show you how to find the population standard deviation if in fact the data is from a population. You need to know that. And it's ever so slightly different. So I am going to start playing this video, and we're going to see, you're going to click in this little double rectangle, and then it's going to tell you open up StatCrunch, and you got pop-up blockers, and then we're going to do summary stats and then columns over there under the stats. We started with stats there. You got to tell it here. If you want population standard deviation, you need to tell it that unadjusted variance and unadjusted standard deviation that I just clicked in there. So, and then I hit compute at the bottom, and here are the results. It gives me the standard deviation. This is S sub x, and again, that's the sample data standard deviation, which is technically what this problem wanted. Okay, I was only showing you unadjusted standard deviation for the purposes of showing you that in case you need it for other data. So that in this case, the population data is not necessary. I wanted standard deviation. It does, by the way, calculate the range, as you will notice, but again, that's not really hard to calculate on your own, and you certainly don't need StatCrunch to subtract for you, so I wouldn't even bother. All right, continuing on this page here, you've got just the definition and some notation for the variance of data. So all we're talking about when we say the variance of a set of data is the square of the standard deviation. So if the standard deviation is S, then the variance is S squared. And that's the sample data variance. And if we're using sigma, because it's population standard deviation, when we square it, we write sigma squared. And so you'll see that is the population variance. Okay? And just one last thing. Right before you square root, back there when we calculated it by hand, you'll notice right before we square rooted, we ended up with the variance. So there's a nice little worksheet here called Comparison of Two Data Sets with the Same Mean. I would like you to work that out. It basically gives you another chance to do standard deviation calculation by hand. But more importantly, perhaps, is it actually gets at what standard deviation tells you about a set of numbers. And that's really important. Truly gets at some understanding of that. Okay, so why don't you read over that little bit there of the empirical rule, something a little bit new for us in this section, and then come on back to me. We'll talk about it on the next page as well. So first off, it's talking about a distribution being roughly bell-shaped. So if we think about a histogram of data, we're talking about a whole lot of data being here kind of in the middle, and then as you get further and further, let's say this is the mean or the center of the data, right? As you get further from the data's mean, you get fewer and fewer observations out there. Heights of people are roughly bell-shaped, meaning many of us are here in the middle near the center, and then as you get taller and taller people, there's fewer and fewer of them out there in there, and true of shorter and shorter people. IQ is another thing that is roughly bell-shaped. Most of us are right there in the middle, and as you get further from the mean, either much higher IQs or much lower IQs, you get fewer and fewer people. And remember that fewer and fewer people is designated on a histogram as lower and lower bars. So we have these three statements, which are going to play a role here in Chapter 3, and then we're also going to see a little bit of them in Chapter 7 when we get back to it. But let's get to a picture more to talk about this mu minus 1 sigma and mu plus 1 sigma, etc. stuff. And we're going to go to the next page for that. But right here, I just did want to talk about this note. Now, I wrote this empirical rule as if this was population means and sigmas. Do you notice that? I was using population. You could have written the exact same thing with X bar and S in place of mu and sigma. So just be aware of that, okay? Going on to the next page now. Okay, first of all, let's address what it means to be bell-shaped, okay? So we are talking about data that perhaps its histogram would look something like this here in my thought bubble. And by this I mean, again, as I said on the last page, most of the data is here in the middle, near to the center or to the mean. And as you get further away from that center, you get fewer and fewer observations, right? And so I could draw a pretty Christmas-shaped bell over that data. That is a bell-shaped distribution. Okay, so now histograms are built in such a way so that the area of, say, this bar, and let's just go with this bar. And I know I'm very talking in generalities here, but hang out with me for just a minute. The areas of those two bars are going to represent the percentage of the data that is in that region, where the whole is 100% of the data, right? And so the empirical rule gives us information about the percentage of a data set that is within 1 standard deviation, 2 standard deviations, or 3 standard deviations of the mean. So let's start talking about that, specifically the empirical rule. So one thing that makes this more easy to understand is realizing that the mean and the standard deviation are just some numbers, right? And we're going to get specific numbers down here on number 3 to help make more sense, of that with a concrete example. But just think of the mean and the standard deviation, just some numbers, right? So here's what we're going to do. We're going to plot the mean, right? Just like on a real number line, we're going to plot some number, right? That's the mean. And then we're going to add 1 standard deviation to it, and that makes mu plus sigma. And then we're also going to subtract that same amount from the mean, and that makes mu minus sigma. And again, on the number line that you're picturing, here is that. Added 1 sigma, and then subtracted 1 sigma. And you got from here to there. And it turns out that amount of the total underneath the curve is 68%, meaning 68% of this bell-shaped distribution will lie between mu minus 1 sigma and mu plus 1 sigma going on. If you start at mu and go 2 sigma standard deviations above it, so you're at mu plus 2 sigma, and again, back from mu, go 2 standard deviations below it, you find this big group. Notice it goes, again, into these endpoints here. Turns out 95% of the data will lie between these two values, mu minus 2 sigma and mu plus 2 sigma. Furthermore, if you go out even further, and again, so I'm starting at mu there in the middle, that's mu in the middle, and I go 1, 2, 3 standard deviations above the mean, and 1, 2, 3 standard deviations below the mean, I get, look at that, all of that. Now you'll see that it's not quite everything, right? There are little tails that I'm not including here. But that, within mu minus 3 sigma and mu plus 3 sigma, is roughly 99.7% of the whole set of data. So that's that very interesting, fundamental empirical rule that we're going to then use on number 3. Now go ahead and read over number 3. A lot of it is done on the next page for us. In fact, basically A and B are done. But read over this, and then you'll go to the next page. So just really quickly, this is data representing the serum HDL levels of cholesterol for 54, you'll notice the 54 female patients of a family doctor. I did consider that population data, and I calculated the mean and standard deviation according to that, and you'll see that on the next page. I also drew a histogram of those 54 numbers. I made StatCrunch make a histogram, and we're going to verify that it really is in fact bell-shaped. And then we're going to do the real meat of the problem, and that's letter C, to try to show you how to organize these things into the empirical rule and how we can use it to answer many, many questions that we will see on the page after that. Okay? Okay, like I say here, I already did A. I did use a calculator, of course. There were 54 numbers, so I stuck them all into my calculator and made it give me my mean and standard deviation. Because I knew it was population data, I did label that mean mu and that standard deviation sigma. Okay, then for part B, tells me to draw a histogram, which I did have StatCrunch do. And question over here in the thought bubble says, does it look roughly bell-shaped? And really, think about that word roughly, okay? We are going to say that looks roughly bell-shaped. It pretty much does follow that. I'm just making it look a little neater there. It pretty much does follow a bell-shaped curve. Again, though, you know, it can be pretty rough, so don't worry about that. Part C says, draw a quick sketch of a bell-shaped curve for this data. And here's what we want to do here. As good a bell shape as you can. Give yourself that horizontal line underneath it. That's like the x-axis on the graph. And then it tells me to label the mean in the middle. So wherever your hump happened to be, hopefully you've made a somewhat symmetric left versus right curve. But wherever the hump happens to be, we're going to label it mu. And that was 57.4. So I'm going to label that like that. And then I'm going to mark various standard deviations, plus or minus 1, 2, and 3, from the mean using a reasonable scale. So all I want to do is say mu plus sigma. Well, that's 57.4. I'm going to add to it 11.7. And what is that? 69.1. And then I'm going to give myself a fair amount of space between that and the mean, just so that it looks, you know, I don't have all the numbers crammed together. I've got 69.1 there. And then for mu plus 2 sigma, well, that's that 69.1 that I had before. Oh my gosh, that's just terribly ugly. Let's try that again. Plus another 11.7. So let's add that in there. What is that? 80.8. And then I'm going to put that here. Now, notice the spacing between mu and mu plus sigma should be the same spacing as I allotted another, because all I'm doing is going down this number line another 11.7 units, aren't I? And then let's find mu plus 3 sigma. Sorry. 80.8, and then I'm adding on another 11.7. So what is that? 92.5, it looks like. And again, another, that same amount of space. Let's label that 92.5. And then we're going to go the other way. So let's do that. So we'll do mu minus sigma, and that's 57.4 minus 11.7. And that gets us 45.7. Again, give us about that amount of space, and let's label it at 45.7. And then mu minus 2 sigma would be that 45.7 minus another 11.7, which is 34.0. I'm going to label that, and I am kind of running out of space, so I'm just going to put my tick mark there a little bit. And then mu minus 3 sigma is that 34 minus another 11.7, which ends you up at 22.3. And so again, just going to give that another bit of space there, 22.3. Now, erasing all of that, I got to get that point back in there. Oh boy, it's hard to write on this thing. You'll end up with your labeled bell-shaped curve, and that's what we want. And we're going to use it to answer questions on the next page. Okay, so what I want you to do here is 3D. This is just rewriting the empirical rule so that you have it on this page so you don't have to keep flipping back and forth in your notes. And then you should be able to do 3E and 3F using the empirical rule. Definitely refer to the graphs so that you see what's going on there. And then we'll go on together and do G and H. But why don't you pause me down here and do 3D, E, and F, and then come on back. Okay, so here is what I did for 3D. All I'm doing was copying down the results from the empirical rule on pages 4 and 5. So within 1 standard deviation of the mean, I know there's 68% of all the patients lie in that region. And 95% of all patients lie within 2 standard deviations of the mean. 99.7% of all patients lie within 3 standard deviations of the mean. And those numbers you'll notice that we came up with for part C when we drew our graph out, you'll notice that they will appear here in these problems. And it's kind of interesting to note that if you did not draw out a curve like part C had you do, you might look at parts E, F, and H and be like, well, how am I supposed to do that? That doesn't make any sense. But having drawn out the curve in part C helps me, because when I get to parts E, F, and H, these numbers all of a sudden look familiar, and that is very helpful. So I will always start one of these problems by drawing out that curve. Even though my math lab won't require it of me, I'll draw out that curve anyway. So let's do E. It says, determine the percentage of all patients that have serum HDL between 22.3 and 92.5 according to the empirical rule. So I again noticed that that was from my mean in the middle. That was mean minus 3 sigma standard deviations. That was that 22.3. And mean plus 3 standard deviations. That was that 92.5. Again, numbers we already calculated because we did part C. And so simply put, the empirical rule says, well, all of that I've shaded there underneath the curve is 99.7% of everyone, of all the patients. And so I made myself a little sentence there. You'll also notice that I don't have a units on that. I don't know what units that we're talking about here with this. It may just be that there are no units, and that's why none were given. It may be that it's just a number, a unitless number. So I don't really know. But I do know the math. And let's continue. If you have not already done letter F, go ahead and do the math on that one and tell me how many patients are in that region. Go ahead. Pause me down if you need to. Okay, so here is my part F, and again, noticing that the numbers that they gave me were in fact mu minus sigma and mu plus sigma. And so automatically I knew that 68% of the patients were in this region. And I did, in fact, you'll notice, include my little pictures over here on this page. I think it's very helpful to see the pictures with those numbers along the bottom and connect that to the empirical rule picture that I've got drawn there on page 5. And so I easily answer that question on letter F. Now, letter G is a little bit different. It is trying to get us to investigate this empirical rule itself. And so what they're telling me is I need to determine the actual percentage of patients that have a serum HDL between 45.7 and 69.1. I'm going to do it by looking at the actual data. Compare this to the answer in part F, which is that empirical rule conclusion of 68%. Okay, so what I really want to do is go back to the data on page 5 and count the number of observations between 45.7 and 69.1. Again, going back to the actual data, pause me down and do this. Go back to page 5 and count. And remember, percent is a part out of a whole. So decide what you're going to divide and come up with an answer for letter G. Pause me down and see what you come up with. Okay, again, I went back to the data on page 5 and I circled every number that was between 45.7 and 69.1. And I got 35 of those numbers. I divided it by the total amount of 54 patients, and that got me, rounding, 64.8% of the patients. So what we're doing here is, again, really just checking if the empirical rule gave us a good estimate. So the actual data tells me nearly 65% of patients are between that 45.7 and 69.1 serum HDL levels. Compare that to the empirical rule that tells me 68%, and I say, yeah, pretty good. Pretty good. Empirical rule did get me a pretty good approximation. So that was awesome. If you want to try H, go ahead, pause me down here and try H. You'll notice the numbers are not quite so cut and dry, so you kind of have to play around a little bit, but I'll let you play around with that and then come back and see what I did. Okay, and on part H, we're back to the empirical rule. Notice they do tell us according to the empirical rule, so that's how you know you're not actually counting the actual data like we did in part G. And so I want this percentage of the patients, right? Who's between 34 and 69.1. And you'll notice I drew those with regard to the standard deviations. So this 34 was mu, that was mu minus 2 sigma, you'll remember, and that 69 was mu plus sigma. So comparing those to the chart on page 5, I am going to say something like this. Well, these two pieces is 68% of the data. I know that from the first part of the empirical rule. Now, if I could only figure out this last bit here, how much is that? But coolly enough, that page 5 picture tells me, if you compare it to that picture at the top of page 5, it tells me that there's 13.5% in this blue region here, this area that I made blue. So to answer this question, I'm going to take 68 plus 13.5% and make, what is that? That's, excuse me, that's 81.5%, it looks like. That's right, of patients have HDL between 34 and 69.1. And that's my answer there. Okay, so kind of had to use the empirical rule, but in a bit different way than we did E and F, didn't we? But you can piece any bits of those together to answer any question that they might throw at you. Okay, last thing, not very important, but we do have the degrees of freedom here defined a little bit for you. Honestly, do not play a large part now. We might see them a little bit later if we get to that stuff in inferential statistics. Really pretty much can ignore that. It's just in the section, so I've got it in here in the notes. So moving on, and we are done with section 3.2. Tell me if you need me. Remember, email me or ask my instructor through my math lab, okay?